Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Anya Nugent with us today. Hello, Anya.
Hello, it's so nice to be here and to be talking to you.
Well, it's so nice for you to be talking about your very lovely article, which we will get to.
Thank you. Yes, no, I'm excited to be able to tell everyone about it.
Cool. Very good. And
Yeah.
Anya, what's your geolocation? Where are you located at?
I'm at Northwestern University, so I'm currently in Evanston.
So it is February
Yeah,
21, 2024 as we record this. And
yeah.
is there any snow on the ground in Evanston?
No, it's
Oh,
57 degrees. It's kind of crazy. I wore my light coat today. I didn't have to put on my winter coat. It was incredible. And just like the sunshine is making me feel so happy. So
spring.
yeah,
Maybe Chicagoland
I
will
know.
be spring, yeah?
I'm hoping this is an early spring and that we don't get any more cold weather, but we'll
Right.
see.
February, Chicago, I think you're probably in for one or
I
two.
know, literally. I think so
It's
too.
it's a good teaser as it goes through. So very cool.
Yeah,
Very cool.
yes.
And Anya, what do you like to do for research?
Yeah, so I study host galaxies of various astrophysical transients.
Okay.
So I'm currently doing my thesis research. I'm a finishing graduate student at Northwestern. And so the majority of my thesis has really been focused on short gamma ray bursts, which come from neutron star mergers.
Well,
Yeah,
I'll do a little, I'll do a little lead here. So Dr.
yeah,
Nugent, when do you
yeah.
graduating, Dr. Nugent?
Yeah, so I just set up my thesis date. It's going to be June 20th.
Cool.
So that is my graduation. That is when I will become a doctor, which is kind of intimidating because I think it's going to be really fast, but I'm also
You
very
will.
excited.
I'm very
Yeah.
excited for you. I think that's
Yeah. Thank you.
congratulations. Congratulations.
Yeah, thanks.
And that is going to bring us to this very awesome APJ article. It is open
Yeah.
access. It's the open access era, people. You can go grab a copy for free. Go get one. A population of short duration gamma ray bursts with dwarf host galaxies. And Anya, take us away.
Perfect. Yeah. So first, I want to thank all of the co-authors that I have on this paper, including my advisor, Wenfei Fong, and then my undergraduate student who's been working with us for the past few years and had some pretty significant contributions to the paper, Christian
Cool.
Castrojón, as well as several other collaborators from all over the Chicago and US area, including Joel Leha, Mike Zebin, and Alex G.
Yes.
So wonderful group of people to work with, and they really helped bring this paper together.
Nice. Good shout out. Good.
Yeah. Yeah. Okay. So now I guess we can get into the
Let's
paper and
let's
all of
go.
the exciting details. All right. So one of the really big questions that we have in astronomy right now are where are all of the heavy R process elements coming from? And this includes things like gold, platinum, and uranium. So after gravitational wave 170817, which was followed by an R process producing kilonova, we understood that neutron star mergers were likely creating a fraction of the R process elements within the universe.
Okay.
However, there's some environments that we have seen within our local group where we don't actually think that that came from a neutron star merger. And this includes things like our local group dwarf galaxies. And a lot of this is because the stars that we see in those local group dwarf galaxies that have been enriched with R process elements, likely that enrichment happened a very long time ago, but on a really rapid time scale.
Okay.
And a little bit too rapid for a neutron star merger, which we typically expect is a little bit more delayed from star formation, takes a little bit longer for those events to occur to create all that R process elements to happen. The
Okay.
other issue is that neutron star mergers experience very large kicks. And so when we're dealing with dwarf galaxies, they're very small. They have small potential wells. Escape velocities are also really small there.
Yes.
And so neutron star mergers have very large kicks that can easily escape a very small dwarf galaxy. And so you could have a merger that goes well outside the galaxy and it could have merged and produce those R process elements, but it could take forever for those R process elements to actually get back into the galaxy and sufficiently enrich all of the stars that we have in there. So this is kind of the setup. Do we need another channel to explain all of the R process enrichment within the universe, or can everything be explained by neutron star mergers? And do we just not have observational evidence of them enriching everything yet?
Fair enough.
So now there is one, so there is one very interesting local group dwarf galaxy, which is called Reticulum 2. It's very small, and several of the brightest stars within Reticulum 2 have high yields of R process elements, which we're pretty sure came from a single neutron star merger event rather than something like a supernova or a core collapse supernova that could occur on a much more rapid time scale and might be creating some of the R process elements.
Okay.
So this was like the basis for our study was, can we explain Reticulum 2's R process yields with a neutron star merger?
Okay.
But how do we actually go out and explore a neutron star merger population? Also, if you want to go to the next page,
Sure.
do this with our population of short gamma ray bursts, since we know that short GRBs are connected to neutron star merger events, which also came from the coincidence of gravitational wave 170817 with a short GRB. And so this is a great population to really study the environments in which neutron star mergers are occurring in, their evolution across cosmic time, because we can detect short GRBs out to very high redshifts, and really get a basis for if they can be polluting all of these different kinds of environments with our process elements.
Nice.
So I'll bring it back a few years ago. I had an initial study where I looked at all of our short GRB host galaxy population and their stellar population properties. This was divided into two papers. One of the papers was focused on associating all of our short GRBs with host galaxies. That was led by my advisor, Wen Fei. We were able to associate 84 out of the 149 swift detected short GRBs with host galaxies, which was the largest population of short GRB hosts to date. And then in my paper, I focused on the stellar population properties of those hosts. Now, one of the things is that I needed sufficient data to be able to model the stellar population properties. And so that required a sufficient amount of photometric data, over 3 bands of photometry. For a lot of them, we had well over that, plus a spectrum to be able to get some beautiful constraints on those properties. Now, what we saw was that there wasn't a lot of evidence that short GRBs and therefore neutron star mergers were occurring in dwarf galaxy environments. So this kind of brings us back to, once again, questioning, did a neutron star merger actually enrich an environment like Reticulum 2? So then I remembered that in my study, I had this requirement for the amount of data to model their stellar population properties, but there was in fact more host associations that didn't meet that minimum data requirement that I had. So out of the population, there were 11 short GRB hosts that comprise some of the faintest host galaxies within the sample that only had around 2 bands of photometry, but they could be indicative of a dwarf galaxy environment. And so this paper was really focused on using novel techniques to be able to understand the stellar population properties of those environments, see if we can connect them back to dwarf galaxy hosts of short GRBs and neutron star mergers, and then use that information to infer what could have enriched our local group dwarf galaxy population.
I'm with you. Very good.
Yeah. All right, so I think we can move to table 1.
Yes, let's look at the 11 hosts.
Yeah. So our host population. Yes, perfect. Yeah, so these were the host galaxies that we studied. We have their locations, the RA and DEC of all of these hosts. The sample refers to how well of a host association that was. So gold means that's a perfect association. There's no doubt in our minds that the short GRB was occurred within that host galaxy. Silver, we're maybe a little bit less confident, but we're pretty sure. And then bronze is slightly less confident, but still within a reasonable range that we're pretty sure that's the correct host galaxy. We also,
I admire the choice of those
thank you.
metals for an R process. Gold.
Yeah, that's a good
Bronze.
point. Yeah. I haven't thought of that, but yes, maybe we'll keep that up for future work.
Okay.
Okay, so yeah. So another cool thing is we can get redshift limits from our GRB afterglow detection. So our GRBs, we have
Yes.
the initial burst and then we detect them in optical, radio, X-ray bands. And
Okay.
so basically by using the bluest optical band that we have and using the Lyman alpha lines, we can place a maximum redshift for all of our bursts, which is going to help in our stellar population modeling, since for a lot of these, we don't have a redshift. But so we need to better understand where in the universe they're occurring. And so this really helps us limit it to the actual redshift constraints that they're in.
Okay.
So we have that in there as well. And then we have all of our photometric data that was available for all of these host galaxies. You'll notice that many of these were taken in different HST filters. And that
Yes.
if you look at the magnitudes, these are incredibly faint. Most of these are 26 to 27th magnitude. They look like little thumbprints on our
Yeah.
images. Like they are barely there. You kind of have to squint and
Like,
see these galaxies. That's how faint they are.
wow.
And then another part of our analysis was looking at the effective radius or the size of all of our hosts, and I can get into that in a little bit, but we
Okay.
also have constraints on their effective radius as well.
Yes.
So then we can go to figure 1.
Very cool. Okay.
Yeah.
Here we go. J-band.
Yeah. Yes. All right, so figure 1 here shows the near-infrared luminosity for the host galaxy population that I studied in my original paper, where we had stellar population property constraints on all of those guys.
Cool.
Those are shown in the gray circles.
Yes.
And then these dashed lines here represent the population that I'm studying in this paper that don't have any redshift constraints on them. So
Okay.
and basically using their optical magnitudes, predicting what their near-infrared luminosities would be at various redshifts.
Okay.
And then you'll also notice 2 of them, which are included in this paper, do have redshifts. So those were some really cool, unique cases where astronomers were able to get on target very quickly and get an afterglow spectrum of the GRB.
Okay.
And through that, they were able to see the underlying host galaxy spectral lines. And so from that, they were able to get redshift constraints for those 2 GRBs, and those are shown in the stars.
Very nice.
So it's really cool. Yeah, what's really cool here is that we notice that basically at all possible redshifts, this faint short GRB population, which is what I will refer to it, is a lot less luminous than the rest of our short GRB population. So a natural explanation for these low luminosities could be that they're occurring in the very high redshift universe, which is really interesting since the high redshift universe was a much younger universe. There was different physics happening at that time. So that could have some cool implications for neutron star mergers. Or if these are occurring at more at lower or more moderate redshifts, then these all kind of fall into the category of low luminosity dwarf galaxies. And that's exactly the population that we're trying to find. So in either case, we had an exciting result that we wanted to go after. So we wanted to get redshift constraints for the short GRB hosts that we didn't have redshift constraints for, and stellar masses to be able to predict where, if these are like indeed a dwarf galaxy population.
Okay, I'm with you.
Yeah. Yes. Okay, great. So I think we can scroll down to our methods now. So what's been really exciting is with the launch of JWST, we've been learning way more about the high redshift universe and galaxies occurring in the high redshift universe, what their properties are, what kind of stellar masses they trace, etc. And in the past year or so, there's been a lot of developments in stellar population modeling methods to be able to constrain the redshifts and stellar masses of very faint galaxies with limited observational data. So like a few months prior to this paper, there was this new code that came out called Prospector Beta, which was intentionally made for faint JWST targets to
Yeah.
pick out potentially high redshift, very massive, stranger galaxies, as opposed to maybe more normal, high redshift, low mass galaxies, et cetera.
Yes.
So what they did for this code, this is the stellar population modeling code that we use in our techniques to model the redshifts and stellar masses for this faint host population, is they fixed the priors of redshift and the mass of the galaxies to what is observed within our universe.
Okay.
So this is as opposed to what normal stellar population modeling codes do, which is making those flat priors.
Yes.
So what's problematic is in those cases when we're dealing with galaxies with very limited observational data, it doesn't constrain the prior enough or the sampling enough
Yes.
to where you're picking out realistic redshift and stellar mass estimates.
Okay.
So what we wanted to do for these guys is when I pick out a redshift and when I say, this is, I want to make sure I'm getting a stellar mass that is actually probable given the observational properties
Okay.
of the galaxy that I'm looking at. So that was kind of a cool update that came out, and we wanted to use our faint host population as a test case for Prospector Beta.
Good. Okay.
Yeah, so and I can go into more detail about Prospector Beta. So it's essentially just a stellar population inference code where you have a nested sampling fitting routine in there that's going over all of our prior distributions.
Yes.
And then it's going to build a model spectral energy distribution and posterior distributions on the stellar population properties of interest, which in this paper, we're really just focused on stellar mass and redshift. Since when we're dealing with galaxies with only 2 bands of photometry, that's basically as much information as we can get. Yeah, so, but I will advertise that Prospector Beta can do a lot more than stellar mass and redshift. It can also look at things like velocities, get you good star formation history. So you should definitely use it, especially for your faint targets. It's just best in this case to only focus on these 2 properties, given the data that we have. Okay, so I wanted to take Prospector Beta a step further. So we can maybe scroll down to the appendix. And I mentioned before that we had effective radii measurements for all of our host galaxies.
Yes.
So the size of the galaxy can actually be correlated with its stellar mass, which is kind of cool. So Prospector Beta looks at the photometry or the spectroscopy, if we have that as well, of a galaxy. And that's just the normal version. But I wanted to include the effective radius measurement, as that can also help us better constrain the stellar masses of all of our hosts. And when we're dealing with such limited observational data, having an additional constraint or an additional parameter where we can say it's likely occurring within this range, not this range of stellar masses, is going to benefit our analysis a lot. So for that reason, I added into Prospector Beta basically just like a likelihood function where I sample from a mass radius relation. And so here what Prospector has done is it's sampled a redshift and then sampled a redshift and a stellar mass. And given that redshift and stellar mass, it builds an effective radius distribution. And these black lines here show where my real effective radius is. And so we can see that it'll determine a likelihood for what Prospector has predicted and say whether or not this was a good fit to the true effective radius, given what the model sampled in redshift and stellar mass space. So we also added this in to test this as well and kind of expand the Prospector Beta framework.
Yes.
Yeah. Okay.
Okay. I'm with.
I think now, yeah. I think we can now go to the results. So scrolling back up.
And 1, 2, and 3. Oh, let's do table 2.
Perfect. There we go. All right, I see it. Okay, so we did both, we tested both prospector beta and prospector beta, including a mass radius relation, just to see how our results varied a little bit. And this is what I'm showing in the table here. We're mainly looking at redshift and stellar mass, but I've also put in what the physical effective radius in kiloparsecs would be for all of these GRBs.
Nice.
So one of the interesting things that we found is that prospector beta typically tends to lean towards lower redshifts than, prospector beta plus the mass radius relation leads to lower redshifts than prospector beta does. This might have to do with the likelihood fits and the fact that at higher redshifts, we get a broader distribution of effective radius values, which will affect the likelihood precision. But overall, we're getting fairly consistent stellar masses between everything, which is great, since one of the questions that we have is, are these dwarf galaxies or are these higher mass galaxies that look more normal to the rest of our short GRB population? So I think the figure, or the figure that's associated with this table kind of goes well with that, where we do, it's the green stars and redshift and stellar mass. I think it may be below this one.
Below, so the first one up is figure 3. These are the corner plots.
Maybe it's figure 5, I think. Yeah.
Oh, okay.
Sorry. I'll go into that, and then I can go into the specific details.
Here we go. Yes, yes.
All right, perfect. Yeah, so I think that this figure really precisely shows how our stellar masses and redshifts change, and what adding the mass radius relation does to our posterior distributions on each of these properties. So we'll see that there does seem to be a decrease in redshifts when we're including the mass radius relation. But what I think is also important is that there's a large decrease in what our uncertainties are when we're including the mass radius relation, meaning that we're finding, exactly. So you'll see like the uncertainties are a lot smaller in that case than they were when just using prospector beta. So that kind of tells us that adding in this additional parameter of the effective radius measurements has really constrained our posterior distributions, and has helped us get better estimates for redshift and stellar mass for all of these host galaxies. Now, it's also cool as looking at this figure, we noticed that these guys are at much lower masses than the rest of our short GRB host population, which once again is shown with the gray circles. And in fact, a lot of these can be considered dwarf galaxies. Typically, consider a dwarf galaxy as less than 10 to the 9th solar masses. And so we'll see that almost all of these guys fall below 10 to the 9th solar masses. So they can all be considered dwarf galaxies. And a grand majority of these guys are even less than 10 to the 8th solar masses. So even smaller dwarf galaxies, which is great. This means that we've found that short GRBs are occurring within dwarf galaxies. So I think if we want to go back up to figure 3,
that's important.
We can get into, do we actually trust these results that I have presented?
That was just an important statement you just made. They are.
Exactly. No.
They are in dwarf galaxies.
Yes. Yeah. So we can do this one. All right, so in this figure over here, I'm showing you 4 different host galaxies that we've done this prospector beta and including the mass radius relation on. The gray distribution here shows the prior distribution. Blue represents when we're including the mass radius relation, and then red is just the normal prospector beta formula, and those are the posterior distributions that we've gotten for each of these GRB hosts. So what we'll see here is that in all of these cases, our posterior distributions do look separate from the prior distributions. So that tells us that we're finding real solutions for all of these short GRB hosts. We're not simply tracing the prior. If we were simply tracing the prior, that would be kind of problematic. That would probably mean that with the limited observations we have, we're not really finding real stellar mass and redshift estimates, but it does seem like these are differing enough where it's really looking at all of the observational properties that we have in there to see what stellar mass and redshifts actually make sense for each of these individualized host galaxies. So if we scroll down to the next figure,
Okay, so there's 4 of them, 5 of them, and then figure 4.
yeah, yes, okay.
Ooh, too
So
special.
we had 2 of our host galaxies that they had redshift estimates from the GRB afterglows. And so these we used as test cases to see how well is prospector beta and our mass radius relation actually finding the real redshift and stellar mass estimates.
Yep.
So another check of our results that we have. So once again here, gray represents prior distribution, red in this case, so we have set redshift as a free parameter. We haven't fixed it to what it should be or what the true spectroscopic redshift is. And so we're kind of seeing what redshift do these methods land on, and what stellar masses do we get when we allow redshift to be a free parameter. And so we're showing posterior distributions here for the 2 different mechanisms we've tried for those cases. And then those black lines represent the median, or where the redshift actually is, the true redshift value. And then when we've set the redshift as fixed, what stellar mass range prospector beta and the mass radius relation are actually finding.
Cool.
And so what we saw in both cases was the stellar mass estimates seemed to be fairly consistent when we did fits where we knew what the redshift actually was. So that's great. Our stellar mass estimates are definitely robust.
Cool.
What was a little bit harder to constrain was redshift. So what we saw in GRB 131004A is that our redshift constraint did seem really good. It seemed to land exactly within the 1 sigma region for what the true spectroscopic redshift is. But for GRB 090426A, it does seem to be the true redshift is much higher than what the median redshift was.
Yeah.
Now we have like a really big assumption in this paper was that our short GRB host population will be tracing the stellar population properties and the observational properties of the field galaxy population. They'll be along the distributions.
Yeah.
So if the galaxy deviates from what we consider normal, then our mechanisms might not be perfect to constrain their stellar population properties. So what we think in the case for GRB 090426A is that potentially it has some observational properties that are different from other galaxies occurring at higher redshifts, and this is why the redshift estimate wasn't as precise. However, stellar mass was still precise in that case. So once again, we have robust stellar mass measurements, which is all we need for our conclusion that these are occurring within dwarf galaxies.
Yes.
Yes, all right. So I think now moving on to figure 6, maybe?
Figure 6, off we go. Figure, yes, there we go. We've got a distribution, cumulative.
Yes, yeah. Yes, okay, great. Yeah, so this is our stellar mass distribution for our entire short GRB host population. So the black distribution here represents that short GRB population that I had studied before with all of the required photometric data and what our cumulative distribution and stellar mass look like. And you'll see here that it's the median was around like 10 to the 9.5 solar masses, and there wasn't a lot of representation of short GRBs occurring within lower mass host galaxies. So the green line here represents what, once we've added in posterior distributions for stellar mass for this faint host population. And we see here that while the median stays the same for our short GRB host masses, there's a much larger increase in short GRBs occurring within low mass galaxies. That tail has extended towards very low mass galaxies. So what's significant here is that we've almost doubled the population occurring at less than 10 to the 9th solar mass galaxies. So this is showing us that short GRBs are more represented within dwarf hosts than we had predicted before, and that we really should be going after using deep imaging to be finding this really faint host population, since clearly it's representative of different environments and potentially going after questions like, are neutron star mergers responsible for all of the R process enrichment within dwarf galaxy or dwarf galaxies?
That is good back. Okay,
cool.
good. Okay.
Implication. Yeah. All right. So the next thing that we did was we wanted to look at other properties of our short GRBs, just the short GRBs themselves, to see, do they look any different from the rest of our short GRB population? I think I like the figure 8 is a little bit better representation of the things that we looked at. So we looked at normal short GRB properties, like their optical afterglows and the offset from the center of their host galaxies.
Yes.
I think I mentioned at the beginning that we expect neutron star mergers to have large kick velocities. And so in a lot of cases, we expect a neutron star merger to migrate from its birthplace and be very far offset from its host galaxy center. So that's a thing that we want to test, where are these occurring within their hosts.
Yes.
The optical afterglow is typically representative of the circumburst environment. So we would think that a brighter optical afterglow could mean that there's a denser environment surrounding where the GRB occurred. So if these are all occurring within the center of their host galaxies, maybe their optical afterglows would be brighter, whereas if they're exploding in the middle of nowhere, maybe their optical afterglows would be a little bit dimmer.
Right.
So we looked at all these properties, changing what the physical offset or the optical afterglow luminosity would be based on the redshifts we calculated in the prospector beta, and including the mass radius case, just to see if they looked any different. I think short story is they don't look any different. The redshift changes are so slight, and your eyes probably can't pick out the subtle differences in these two figures.
Right.
So what was interesting is, so almost all of the short GRBs occurring within faint host galaxies did have optical afterglows, which is a little bit different from the rest of the short GRB population, where only about 30% or so of them have optical afterglows. But when we look at their luminosities, they do seem to be fairly consistent with the rest of the short GRB population. Now, we actually took this as a good thing, because if their luminosities were much higher than the rest of the population, it might mean that we were predicting too high of redshifts. And if they were much lower, then that might mean that it would be too low of redshifts. So we take this correlation and consistency with the rest of our short GRB population as a good thing. We're likely finding the correct redshifts, or we're around the correct redshifts for all of these guys. Now, what is cool and very fascinating is when we look at the physical offsets, we see that all of our short GRBs in the faint hosts are occurring at much smaller physical offsets within their host galaxies than, so within the in comparison to the rest of the so occurring in a lot more central locations. So that was kind of a cool implication. They do seem to be tracing a slightly different environment. And I think if we go to the next figure, we highlight this with our cumulative distribution.
Figure 9. There we go. There's cumulatives. Okay.
So in this figure over here, green represents our faint host population, and black represents all of the other short GRBs and what their physical offsets were. And so we see very definitively here that short GRBs in this faint host population are occurring within way more central locations than the rest of the short GRB population. Now, the purple dashed line here represents all of the other short GRBs that I had studied originally that occurred within less than 10 to the 9th solar mass galaxies. So looking at our entire dwarf host galaxy population, and we see even there that they're occurring within more central locations within their host galaxies.
Definitely.
Now, another thing that we can test is we can normalize our galaxies by their size, or the offsets by the size of the galaxy, to see how far within their hosts are these guys traversing. So that's the final panel on this figure 9.
Blows
And
one.
so what we see here is that even when we're looking at the host normalized offsets for our faint host population, is they're occurring within even smaller locations
Yeah.
or from their host centers than the rest of the short GRB population. So this is definitive evidence that our short GRBs within dwarf galaxies are occurring within more central locations within their hosts than the rest of the short GRB population. And I think that brings us to what's the big point? Why does all of that matter?
Our process.
Yes, exactly. That's like the big main conclusion here. So we have really shown with this paper for the first time that short GRBs and therefore neutron star mergers are very represented within dwarf galaxies.
Yes.
Now, the other cool thing is that because our short GRBs within dwarf galaxies are occurring within central locations, it means that they're capable or very capable of enriching those environments with our process elements, which is a cool implication. And that's kind of what we want to study. These aren't exploding way off in the middle of nowhere where we can't say whether or not those elements can get back into their host galaxies.
They won't.
These are occurring centrally.
Correct.
Yeah. Yes. So that's a really like cool implication that we now have observational evidence that neutron star mergers are likely contributing a fraction of the R process elements within their hosts to the universe. Yeah.
Well said.
So where do we take this next, or what can we do? So one of the things that we weren't able to study within this paper was the star formation histories of the galaxies, and that was because we didn't have the observational data to be able to constrain those star formation histories. Now, what's important about the star formation histories is that gives us a better understanding of when all the stars formed, and we can use that to estimate the merger timescale of these systems. So what we would want to do is eventually get information that would help us constrain these star formation histories, and then use that to get merger timescales. And if all of these guys are occurring on very rapid timescales, it could mean that neutron star mergers are the dominant source of our process elements within dwarf galaxies. And really, at that point, it would be all galaxies at all stellar masses. And would help us better answer, do we actually need other mechanisms to be creating these heavy R process elements, or is neutron star mergers enough to explain all of the R process abundances that we see within our universe?
It's a very interesting question.
Yeah, yes.
Very good.
Yeah, so I think that's kind of all that I had on that paper.
Very cool. Very cool.
Yeah.
I want to thank you so much for walking us through your very awesome APJ article. Thank you.
Thank you.
And you touched on it a little bit there at the end, so let's push on it a little bit. I'll see where that goes. So where do you think we go from here, given the current study? You mentioned a little bit about other ones. Do we have any hope of increasing the sample size by an order of magnitude, let's say? Is there other work that could be done with the theoretical models? Hopefully we get another GW event.
I hope so.
Yeah, that would be nice.
Yeah.
So where do you think we go with this, let's say, over the next couple of years?
Yeah, so we definitely hinted a little bit at this in the paper, but I think getting JWST spectra of these host galaxies is going to be really important to constrain their redshifts to get star formation history, so we can get merger timescales and better understand the rates of neutron star mergers within dwarf galaxy hosts, how much they can actually be contributing to those environments, if they are occurring on rapid enough timescales to explain all of the R process enrichment that we see. So I think that would be a really exciting avenue to go next. I also think continuing to follow up on our short GRB population and really advocating for more instruments and satellites to go up in space. As things like Swift are unfortunately dying and probably will not be around in the next few years. But I think that this is really exciting. Short GRBs tell us a lot about how our universe has evolved and the chemical enrichment of our universe. So continuing to follow up these guys understanding their host galaxy environments, where they're polluting the universe with our process elements, highly important for us to piece together everything about how we came to be.
Got here.
So I would definitely say they're exciting avenues. And then I think getting a better understanding of how systems are able to enrich environments with our process elements. And that's something that I'm currently exploring, is thinking about using our short GRB population to better understand when after the burst can environments be enriched with all the elements that they're producing.
Very cool.
Yeah.
Very cool.
Yeah.
Somebody's going to have an awesome thesis.
I hope so. Yeah. Thank you.
Cool. Anya, thank you so much once again.
Yeah.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you. Bye.